Today, in this video, I'm going to explain some few important questions that are the main reasoning questions of chapter number 3, current electricity. The first question is, three resistors 1, 2 and 3 ohm are combined in series. What is the total resistance? This is not a complicated question. Answer would be 3 plus 2 plus 1, that is 6 ohm, because it is a series combination. The second is, what happens if the galvanometer and cells are interchanged at the balance point of the meter bridge? Would the galvanometer show any current? Now this question means, when we have learnt about meter bridge, there are two things here. There is a galvanometer, there is a cell. After finding the balance point, if you change their position, the question is, will the galvanometer show any deflection or show any current? The answer would be, see, on interchanging the position of galvanometer and cell, the balance point is not changing, so it will show no current or it will show no deflection. When galvanometer and cell are interchanged at balance point, the galvanometer shows no deflection, hence no current would flow through the galvanometer. Next is, a steady current flows in a metallic conductor of non-uniform cross section. Which of these quantities is constant along conductor? Current, current density, electric field, or drift? So in this question, there is a conductor of non-uniform cross section, and the question is, which of the quantities will remain same or will not change or will remain constant? The answer would be current, because other quantities like current density, electric field, drift speed, they all depend on area. They all depend on area of cross section. The only quantity that does not depend on area of cross section is current. So when a steady current flows in a metallic conductor of non-uniform cross section, the current flowing through the conductor is constant. Current density, electric field and drift speed are inversely proportional to the area of cross section, therefore they are not constant. Next is Ohm's law universally applicable for all conducting elements? If not, give examples. When we studied Ohm's law, we studied about two types of resistors, ohmic and non-ohmic. Non-ohmic were the ones who do not follow Ohm's law. So answer would be, it is not universally applicable, and answer examples would be vacuum diode, semiconductor is a non-ohmic conductor. Ohm's law is not valid for it. Next, a low voltage supply from which one needs high current must have very low internal resistance. Why? Now this is again a very good reasoning question. A low voltage supply, that means V is very low and you need high current from it, and the formula of I is equal to V by R. Now if V is small, okay, V is small, V is equal to IR, I is equal to V by R. If V is small, so current is automatically small, but you want very high current. Now to find very high current, R and I are inversely proportional, then in that case R has to be very low. So that's why a low voltage supply from which one needs high current must have very low internal resistance. Next is a high tension supply, say 6 kilovolt, must have a very large internal resistance. Why? In order to prohibit the current from exceeding the safety limit, a high tension supply must have a very large internal resistance. If the internal resistance is not large, then the current drawn can exceed safety limits in case of a short circuit. So large internal resistance limit the value of electric current flowing through the wire, so that it does not lead to any short circuit. So that's why a 6 kilovolt, a high tension wire, must have a large internal resistance.